why I was feeling like things were a little weird. Oh, that makes sense.
Yeah. Okay. So, but yeah. So I don't know which chapter things are in. Yeah. There's one big problem coming up, which is the complex scalar field. So how far did I get last time with the scalar field proposition?
With the new one, we had just gone up to the end of part 1, where we had found the full solution to the classical.
The full Fourier solution. Okay. Yeah. All right. That's what we needed then. All right. So and then did we do the energy integral and get it as a 3-dimensional Fourier transform?
I don't remember. Let me look here in my notes. Doesn't look like it. I think we were just about to start.
Okay, so it's still a 4-dimensional integral? So
no, it's just no, it is a 3. We did do the part. Yeah.
So you've got a Dirac delta over energy. We're setting the energy positive by hand.
Yes. We did do that part. Yeah.
All right. We did
do that one.
Good. All right. So from there, yeah, that's good. That's easier to write. Okay. People coming in fast and furious here. Good. Good to see you all. This is a fun group that's nicely relaxed. We just do quantum field theory. Okay. Anybody have any questions before we just launch into it here? I think what we had was this solution for phi of x and t. As there's a coefficient here, what, 2 pi, to the 3/2. And oh boy, it does take, and how do I do this? 3k over root 2. Okay.
We left with the wave number terms. Yeah.
So we have psi x plus a conjugate ik. So nice Fourier transform, 3 dimensions, integrate over all k with a, here comes line, good. With a, some convenient coefficients. Turns out those will be the right sort of coefficients to write. So I think this is where we left off. Can you see the green okay? Is that showing up all right for you? Okay, good. So what I want to do, we're going to quantize this, and ultimately we're going to show that this A and that A conjugate become A and A dagger and act just like this simple harmonic oscillator one says, raising and lowering operators. That's where we're headed, but I want to do this in a way that makes it clear that that's pretty much the only thing you can do here. We've done canonical quantization to the point of putting hats on phi and its conjugate momentum pi. And we have a fundamental commutator for those guys. But what I want to do now is invert this Fourier transform and solve explicitly for A of k and A star of k. And you'll see that that expression is a Fourier integral over phi and pi. And when phi and pi become operators, the only way that that can be consistent is if these become operators too. Moreover, what happens is that the fundamental commutation, the fundamental commutators for phi and pi imply certain commutation relations for A in what becomes a dagger. And those, it is going to look just like the simple harmonic oscillator, but for each K. But going through it is pretty typical of what we have to do in these sorts of calculations. So wait a minute, what did I do here?
Quick question here.
Yeah. Oh, I see the time dependent one here. Yeah. Let me write these differently. In the notes, what I've got is, yeah, it should be plus I. So this is minus I omega t minus k dot x. So this one's positive on the k. And then this is the conjugate. Sorry, so what was the question?
The question was, I just wanted to make sure the alpha index that goes over all 4, 0 through 3, or is that just space?
Which index?
Alpha? Wasn't there? Is that an A alpha index, or am I reading that wrong?
I don't see an alpha. Oh, here?
Yeah, I read that wrong, I guess.
That's complex conjugate.
Never mind.
I'm trying to do an asterisk there and a little unsteady it.
That makes a lot more sense.
Okay, it's just,
I don't know.
Yeah, the second term is exactly the complex conjugate of the first because it's a real scalar field. Now, I've set up a problem for you guys, another section a little further down, do the complex scalar field. So everything I'm doing for the real field, I want you to do for the complex field. It's a long problem. There are a lot of steps to it. So I've called it problem 1 as opposed to exercise. And it'll take you a while, so get started on it. After we do some of this, so you see where to go. But for a complex scalar field, you're going to call this B conjugate, not A conjugate. So this does not have to be the complex conjugate of that. It introduces twice as many independent degrees of freedom. And so phi and phi conjugate will be different fields. They'll each have conjugate momenta. So you'll be working with 4 fields instead of just the 2 that we'll do here. And yeah, give yourself lots of paper or computer room or something, however you guys like to work.
A lot of paper.
You work on paper? Yeah, I used to. I've got notebooks and notebooks and notebooks of, handwritten calculations. But now I do all my calculations in a LaTeX editor, where I can just copy lines. It turns out to be faster for these long expressions. Okay, so I'm doing it I'm explicitly solving the classical theory for the A and A star so that when I quantize, we see that there's no other option for quantization than quantizing the mode amplitudes. So then what we do is we take the inverse Fourier transform here, 1 over 2 pi to the 3/2 integral phi, and it is sufficient to do this for t equals 0, I think. Let me check this one. Some of these you do with t equals 0 and some you don't. And I think we're fine. Yeah. For solving for these, we can take it at the initial time. So just phi of x. Phi of x, by phi of x, I mean phi of x and t equal to 0. Then e to the minus I q dot x d cubed x.
Dr. Buehler?
Yes.
I'm so sorry to do this to you, but I think I see a typo.
Okay, where in the book
in the book? Yeah, I'm so sorry.
Okay. No, that's fine. Bound to be.
It's the inline Fourier the inverse Fourier expression you gave. It's section 4.2 and the top of page 116. You have ik dot x instead of minus ik dot x.
Minus I So the inline,
In the paragraph.
where? Still
Top
in
of page
above
6.
4.3. So top of page 116.
Yeah.
And so tell me again, what's the problem?
The exponential.
Yes.
E to the ik dot x.
The ik dot x.
It's the very first thing on the page.
Literally the first line.
What version of the book are you looking at?
February 22nd.
Okay. Yeah, I don't see what you're talking about. I don't have an e to the ikx except for the inline equation 4.4. Or it's not inline. I mean the set apart equation 4.4 is phi of x and t, which is what I've written here.
Next page.
Next page. Okay, so in the first paragraph of 4.3.
No. So it's be above, it's on the page with 4.5 through 4.10.
It's the first paragraph when you introduced section 4.2.
Oh, I may have edited this since you guys got that update.
Oh no.
Oh boy. So we may be looking at different versions. Maybe I caught this. So what is the issue? What does it use?
It's a positive ik dot x when you're using negative ik dot x when you're doing the inverse Fourier transform.
Oh, okay. So what I have at the beginning of solving, for the Fourier transform, multiply phi by 1 over 2 pi to the 3 halves e to the minus I k prime dot x.
Yeah, you fixed that then.
I fixed it. Okay. All right. Yeah. So from here on, I'm working off notes that you don't have. Sorry. Yeah, I could take 5 minutes and post this, but let me just work through. But yeah, wait till I post this version before sending in errors. But yeah, there were some. I found some things that I changed. All right, so, and I'm going to call it Q here instead of K prime, although it's still K prime in the notes. I'm trying to avoid using too many primes. It's just, it makes the look of the equation even messier than it needs to be. So, okay, when you multiply these two coefficients, you get a full 2 pi cube, which is the normalization that you're going to want when you create a delta function. All right, the integral of a pure Fourier e to the ikx is 2 pi times the delta function. So you're going to get 3 factors of 2 pi, and that's just what you want. So inverting the Fourier transform, I always put a root 2 pi in front of each one and in front of each inverse. People do that differently. But then, what do we have? We've got d3x, d3k, root 2 omega, a of k, e to the, and now we've set t to 0, so I just have I k minus q dot x. And let's just write plus the complex conjugate here, so I don't have to go buy another board. And now we can integrate that. Yeah, be careful about taking shortcuts with these because, each one of these long things where you get all these delta functions has slight differences. And you really need all your signs to work out or they don't. Okay, so we interchange the order of integration here. So now we're integrating this pure Fourier mode, and that's going to give us 2 pi times the delta function, so it cancels this coefficient, and we're left with d3k over root 2 omega. Then we get a delta, we have a of k delta of K minus Q plus a conjugate of K. And here we have either the minus IK delta, so it's going to be delta of K plus Q. And that's the three-dimensional delta. Any question there? Good, okay. So you integrate, and we get 1 over root 2 omega, then A of Q plus a conjugate of minus Q. All right, and we see that the Fourier transform of the field is not enough to determine A yet, because we're going to need the momentum. So we have to do the same thing for the momentum, which follows from phi. Remember, the momentum is phi dot. So that's going to be 1 over 2 pi to the 3/2 d3k over root 2 omega. Then what we need is, all right, we're going to get a minus I omega when we differentiate here, plus I omega there. So if I write that as, let's pull out a minus sign here. Let's pull out that. Let me just put the minus I here, and then the omega has to stay inside because omega depends on K. Then other than that, all right, I had a minus I omega here, so this one is still positive, A of K. But there's a relative minus sign here because we pulled down a positive I omega. So we get plus the conjugate A of K here. And I've left off my exponentials. Whoops, sorry. E to the minus I omega t minus k dot x plus a conjugate k e to the I omega t minus k dot x. And close paren. Yeah, I spent all day yesterday working through these notes. I'm almost done with the new chapter 3, which includes up through conservation of the current for the charged field. I'm basically rewriting the whole stupid book. I wrote it so long ago that, there's some things that need tuning up. So I hope I can keep ahead of you guys. All right, so now we do the inverse Fourier transform of this one at time 0. So we get 1 over 2 pi to the 3/2. The integral of pi of x at time t0 is minus I q dot x. And let's see, can we just go all out here? And we know what delta functions we're going to get. So I think we can probably get this right. d3k, then this becomes root omega over 2. And then this one is going to get a delta function in plus k minus q. So when we integrate over d3k, this is just going to become A of q. Then this one, let's see, this is minus. Yeah, so we're going to get minus A conjugate, and then it's minus K minus Q, so we're going to end up with a minus Q here. And then between the two of these, we can solve for A and A star. Okay, so let's see about writing that solution. I'm going to keep phi up top. We probably keep needing it. Right, so if I add, now let's see, I want to write A of Q, and if I multiply root 2 over omega here and root 2 omega I just erased the, oh, here. This is the transform of phi. Then these can just add and the A star drops out, but I'm going to have a factor of 1/2. And I'm going to pull out the 1 over root 2 omega here so that I get, all right, that's the transform of phi. So 1 over 2 pi to the 3/2 integral phi of x e to the minus I q dot x d cubed x. Then I'm adding, so I need to put the root 2 pi, 1 over root 2 pi times root omega over 2, looks like it gives me 1/2. Can I get 1/2 there? Let's see. Oh, sorry. I multiply by the inverse to this on this side. So I get a root 2 over omega, but I'm pulling out. I'm doing too much in my head here, sorry. But I'm going to have a factor times the momentum integral. 1 over, I'll look up what I did in my notes here. Sorry, just hang on a second. E to the minus I q dot x. So it's the same Fourier transform for both of these. I just need to get this coefficient. And what is that coefficient? Yeah, I over omega is what it turns out to be. So yeah, this coefficient is I over omega because there was an I, because of this I and pulling out that omega, I get a full omega here. Huh. That seems funny, but let's so it's a Fourier transform, d cubed x e to the minus I q dot x. And then the part inside is phi of x plus I over omega pi of x. Yeah, sorry to crowd this so much. This is one place where I really like to be in the classroom where you've got like 2 or 3 long boards end to end. It's takes a little more planning right here. So this is what I got when I worked it out carefully. There should be a 2 pi to the 3/2. And all right, okay, I see what happened. Yeah, there's a 1/2 because I get 2 of these guys when I add the 2 equations. Then I get a normalization for the Fourier transform. And then overall here, I have a root 2 omega in the numerator. So that's A of Q. Then the conjugate is 1 over twice 2 pi to the 3/2 d cubed x e to the, it'll be plus I q dot x. And then we'll have root 2 omega times phi of x minus I over omega pi of x. Okay, so the Fourier transforms of those combinations. Okay, yeah, this is the kind of calculation you want to step way back and be very careful. But all right, so we've got this, and now we can turn these things into operators. So yeah, this all looks right. And so now at this point, we can put hats on everything. So if I write A of Q here, we know that those guys become operators and the complex conjugate becomes the adjoint. Here, this all happens because phi and pi are actually our known operators here. We know how they commute. When those become operators, this is an ordinary Fourier transform of operators. It's going to give an operator. So this shows us that, let's see if I can, there. It's neater in LaTeX. All right. So this is in the new notes, carefully written out. I will post those. Let's see. Well, soon. I'll try to get them up this afternoon. But these are now correct, I believe. And what we wanted to,
Professor?
Yes, question.
Yeah, I'm sorry, but I was following along on my own on my
Okay. That's
on
fine.
my notebook,
Good.
and I'm getting that the minus sign for the momentum operator is on the A operator, not the A dagger operator.
Well, let me see.
And that's because we had the I on the bottom, and we want to put it up. You pick up a minus sign there.
All right. Yeah, you may be looking at my old notes. Did we have the same starting point? Yeah, this is a
Possibly,
sign.
sure.
That's a sign that changed when I redid these notes. So yeah, that suggests you're doing it right. Okay, but you're doing it right in a different convention. I think I've done it correctly here for the way I've got these fields defined. Now let me look a little more closely, because yeah, the thing is, a conjugate. All right, they're clearly conjugates of one another. So the question is, do we get wait a second. So phi is A of k times the Fourier thing plus A star of k. So the delta function puts the argument of A star with a minus sign. So I get A of k plus A star of minus k here. I get a minus sign inside. Are you seeing that too, or?
Yeah, no, that's fine.
Is that where we see a difference?
No, that's fine. It's the I'm not sure how we got different results.
What expression for phi did you start with? Okay, I'm looking at. Let's see. So do you have these signs in your solution for phi?
Oh yeah, that's fine.
Yeah. So we agree there. So when we take the Fourier transform, Yeah, so now I see. It's really though from the solution. All right, so the Fourier transform of phi looks like, yeah, so we're going to bring this root 2 omega over here. This is going to depend on that sum. You agree there. Then the momentum, let's just do a quick check here and see. All right, so for the Fourier transform of the momentum, let's see, we pulled down a minus I omega. So over here we have minus I omega over 2.
Right, that squares away.
Then A plus, then A minus A star of minus K, right?
All right, that's
Like
it.
this.
Thank you.
This is basically pi, the Fourier transform of pi. So we're going to have 2 over omega multiplied by a plus I to get rid of that whole coefficient. Right, so that's gone. So now I add these two to get rid of the A star. And so it's going to be phi plus I pi. So I'm sticking by what I wrote, I think.
Yeah, it looks good. It was that minus I in the beginning.
Yeah, it's worth arguing about this because it makes an important point. These things are touchy. It's very easy to get a sign off, to get a factor to pi, never mind putting in the factors of Planck's constant. You know, when we compute the Hamiltonian operator, well, which we're going to do here shortly. All right, it's an integral of pi squared plus grad phi squared plus m squared. You have to do, each of those is an integral over products of 2 of these field expansions, you know, with derivatives, you know, factors of ik or minus ik or m squared or whatever. In the end, if you don't have all those signs right, you know, the wrong things will cancel. Your Hamiltonian will have time-dependent exponentials in it. You know, 2 terms have to exactly cancel, and the other 2 have to add up to the energy squared, twice the energy squared. You know, if that doesn't happen, oops, you've got a mistake somewhere. It's tricky to get that all right. Okay, so you know, pay attention to this exercise. This is not an exercise. I call it a problem, and I make it a whole section, right? And I give you benchmarks on the way through the problem so you can check your work, check your signs. But you know, this stuff takes some real care and a lot of paper. So I'll go with the plus signs here. I think we may agree now, but in any case, let's press ahead. The next thing to do is find the commutation relations for A and A dagger. Let's see. So here are the operators. All right, by field. We want to work with A and A dagger now. Unfortunately, those are right in the middle of everything, but I want to compute A of K with a dagger of probably Q. Let me check my notes on that. Yep, that's just what I did here. So what this is this turns into a commutator where we have we have two normalizations, so I think we're going to get a 2 pi cubed here. So we get that. Looks like we get a quarter. And then we're going to have integral d3x, and let's call it d3y. And then we're going to have a commutator of, now let's see. Oh, okay. Yeah, the Fourier mode is going to be e to the minus I k dot x plus I q y times the commutator of this stuff, phi hat plus I over omega pi hat with a root 2 omega. I'll pull the root 2 omega out. And then we have phi hat minus I over omega pi hat. These guys are at y, these guys are at x. And then we have this root 2 omega, and that's omega to k. In a dagger, we have a root 2 omega q. Remember, those are different. This one is an omega q. This one is an omega k, I think. So you've got to keep your notation clear here. You know, ultimately, all the k's and q's come out the same because we're gonna do. Let me think now. What integral do we do first? Oh, now we evaluate this guy first, the commutator, because we know that pi with phi, we're going to get 1 over I omega k. Then this commutator is going to give us a del 3 of x minus y. Remember, this is at y. And I believe an IH bar, which will give us sine. Then the other one, this is omega k. The other one is minus phi with pi. Oh, pi with phi is minus this. Pi with phi is going to give plus that. So we're going to have I over omega q. Then this is a minus I over, wait a minute. Minus I over omega q. Then phi with pi is I h bar del 3. There we go, x minus y. The two give the same thing. We get a factor of 2, and it seems to me that should have been a 2, but it's a 4. I'm not sure why. Oh. This commutator gives us a 2, but I shouldn't have a 2 here. Oh, rats. I have a 2 here in my notes.
You have the root 2 omegas, right? You can take out the root 2s with the omegas.
Root 2 omega. Oh, that's going to give me the other one. Yeah. Okay. Okay. Yeah. Yeah. So one of them is here, and one of them is because I get 2 of these things. Okay. So let me tip you down. So here we're looking at a hat of k with a hat dagger of q. And let's see what happens. So there are 2 of these. This is plus, this is plus. The fact that you've got a delta of x minus y, the fact that we've got omega of q on one and omega of k on the other isn't going to be a problem, because this delta of x minus y makes this an exponential of e to the minus I k minus q dot x, which when we do the x integral is going to give us a delta function in k minus q. So the 2 pi cubed will go out from that delta function. So here's what happens. We integrate over y, that sets all the x's equal to y, or the y's equal to x. Then we do the integral over x, that gives us a delta of k minus q. And at that point, these omegas become the same. So let's see, so we've got 1 over omega. These omegas become the same. So we get just 2 omega k, let's say. That's going to cancel these guys. So these omegas cancel those. The 2 here and the 2 here cancel the 4. And we're left with something, right? The 2 pi went out, the 4 went out. This gave us a delta k minus q. The exponential's gone in the delta function. These guys, we integrated over that delta, and the i's squared to plus 1, the 2's are gone, and we have an h bar, I think. Although, you know, that h bar shouldn't be. Let's take h bar equal 1. That was a dirty cheat, sorry. But if you track through the units, you won't end up with an h bar. All right, let's see. Yeah, I put it in because I assumed it was there from the commutator of phi with pi. But you know, I've probably taken it to be 1 somewhere else. But if you put your h bars in at every step of the way, they work, I promise. So this is actually the answer, right? This is the thing that comes out of a careful working at this, and I think I've shown you the at least the issues that come up with getting the cancellations right. The commutator of A with A dagger is 1, except we have a continuous parameter k and q, so it's 1 if k equals q, except it's 1 under an integral sign. So the only real difference we're seeing from the simple harmonic oscillator here is the continuum dependence of the raising and lowering operators means that their commutator gives us a Dirac delta instead of just giving us, well, if we had multiple harmonic oscillators, you know, 3 of them or something, you'd have a Kronecker IK, a delta IK of some sort. So, so this is good, and this tells us how to interpret states. You know, what we do from here is, well, still a lot more work, trickier stuff, in fact, because now we need the Hamiltonian. Once we have the Hamiltonian, we can use this commutator to show that A and A dagger actually do act like lowering and raising operators, the same as the harmonic oscillator. Having that commutator give us essentially 1 is what does that. And the sign there is crucial. You want A with A dagger, not A dagger A, or A dagger is going to lower states and A will raise them. So you want to get that right. So now, in order to really show that we can construct states the same way we do in quantum mechanics with the oscillator, the next thing we need is the Hamiltonian. If we have the Hamiltonian as an operator, now we can define eigenstates of the Hamiltonian and show that H acting on A acting on an eigenstate gives an eigenstate with lower energy, right? It's the same idea of the proof, only at every step of the way, we're squaring these big Fourier expansions. So, you know, we've got a Fourier expansion for well, everything in sight. Right. yeah, let me write the Hamiltonian. Before I jump in with the Hamiltonian, is there any question here? You guys can carry this through. If you're working with pen on paper, you can be a little more careful than I'm able to be on the board, but it really does work. It takes a while to get your conventions right. Be sure you're getting your factors right. I think I've been careful in what I've written up in the book so far. So let's look at the Hamiltonian now. So this turns into simply delta of A minus Q. Now, you remember the Hamiltonian. We started there. It's h bar, is it h bar over 2? Yeah, h bar over 2. Yeah, there's a half on everything. All right, integral pi squared plus grad phi dot grad phi plus m squared phi squared. Simple, right? Okay, there's our Hamiltonian. Now, the Hamiltonian operator. Still simple, right? Okay, except we have a Fourier. If we want to write H in terms of A and A dagger, we're going to have to square those Fourier expansions for these guys, do all this same kind of delta function stuff and resolve it. And the thing that you really have to be careful with here is the sum of these three terms. Okay, a grad is going to pull down plus or minus ik. Pi is a time that's going to pull down omega squared. You're going to have like I omega squareds here. You're going to have plus or minus ik dot plus or minus iq, depending on how your signs sort there. This will be an omega k times an omega q, except eventually there's a delta function. Here you have an m squared times some stuff. All of that is going to factor out. You are going to have three terms. You're going to have an A dagger term. You're going to have an A term. You're going to have an A dagger A term. You're going to have an A dagger term. All right. And you get, in front of each of these terms, you get a sum of these three with different signs. And these guys have an e to the 2i omega t. These guys have an e to the minus 2i omega t. And the Hamiltonian is not time dependent, so these had better go away. Well, they do, because what you get is omega squared minus k squared minus m squared times those two terms. That drops out. That's zero. That's your energy condition. On these cross terms, you get omega squared plus k squared plus m squared, which is just twice omega squared. That's a 2 there. So these cross terms come out with a factor of 2 omega squared times, I don't know what Fourier stuff. Let me just scroll down here. I've written this all out. I'm not sure. You know, I can do one of these for you, but it's the same kind of thing where you have you have 9 integrals, right? You have d3x, d3k, d3q. You're going to interchange the d3x with the momentum integrals, and you're going to get some sort of delta function. And that will turn something else into potentially a delta function. You gradually do all 9 integrals. And let's see, well, no, you end up doing 6 of them. Let's see, and yeah, I did these faster and faster. Okay, I really need you to read this, but let's see. Yeah, what I'm telling you so far is true. looks like the overall coefficient, like for the m squared term, I get the h bar over 2, I get an m squared, and then there's a d3k over 2 omega that comes in. And then, let's see, how do we show that? Yeah, it's putting them all together that things go away. Let me you know, rather than, you know, we can come back and I can do, you know, one of these integrals for you. But I think you probably get the gist of how you work through them, delta function, integral, delta function, and boil it down. What you get is the following thing for H. So, so you do all of that. And you get something that actually looks like it makes a lot of sense, and it almost does. So miracles happen. And you find that H is given by, let me just write it as D3K, H bar omega. Then let me see which way. A hat of K, A hat dagger of K, plus A hat dagger of K, A hat of K. So you need to work through these integrals. You need to know how to do it. I'm happy to go through it if you need to see that all done. But let me talk about something that's a little more interesting / disturbing / magical / actually makes pretty good sense. This Hamiltonian, if I act with this thing on states, you know, this is going to raise the states, this is going to lower the states, and you know, it's not really clear what's going to come out of that. If I want this thing to have a vacuum state, I want all my lowering operators on the right. And incidentally, while we're on that, these things are not called raising and lowering operators here. They're called creation and annihilation, because in the simple harmonic oscillator, you create one quantum of energy of your spring system, right? And now you have 2. And now you have 3, and so, wow, that looks really cool on the screen. It's sort of like a strobe light. But here, when we create a state with, you know, 1 excitation with wave number K, it's called a particle. And we create another. Now we've got a 2-particle state, and pretty soon, you know, we've built Alex her whole Fox space of states. And so instead of calling them raising and lowering, we call them creation and annihilation, where they create a particle or annihilate a particle state. Now, if I use the commutator here, there was a 2 here. This 2 matters. But if I commute this pair, A dagger, I can write as.
Need a screen check.
Or check, yeah.
Sorry? Oh, yeah, sorry. Got it. D3K, can you see now? Then that cancels the 2. So I flip these guys, and I'm going to get A dagger A plus this delta. So the 2 cancels. So then I have A hat dagger of K, A hat of K, and then plus a half, because the 2 only happens on here, delta 3 of what? Well, they're both K, so it's really just delta 3 of 0, and that's our Hamiltonian operator. Now, by my counting, I do this integral over all k in 3 different directions. Each of those gives me twice infinity. So I get that cubed, then I have a half, and then delta of 0 is infinity, so I get another infinity cubed. This is a somewhat divergent term. Okay, yeah, up to factors of 2, it's infinity to the 6th. Not good. What do? This is where we introduce the idea of normal ordering. All product operators now are going to be normal ordered. That means you, in the definition of the quantum operator, you put colons at the beginning and end of the expression in terms of the fields. So we're not going to take the Hamiltonian operator to be this. We're going to take it to be this. Okay, that denotes normal ordering of the operators, and normal ordering is defined in terms of the the creation and annihilation operators. It means put all the annihilation operators on the right. That means that normal ordering of this is already that. So normal ordering this, we don't use the commutator, we eliminate the constant term. And that works anytime you've got operator products for these fields. Now, you know, gravity, who knows what happens? It's nonlinear, you know, things aren't going to be this nice. But for Dirac fields or scalar fields or vector fields, E and M, you just normal order all field products. Every time you have a field product, we're going to end up defining creation and annihilation operators because the mode amplitudes always get quantized, and they annihilate or create particles. And we're going to put all the annihilation operators to the right. Your right, not my right. So that eliminates this term. This is the first infinity you encounter. This is not the last infinity we'll encounter doing like QED, but we normal order all of our operators.
Professor?
Yes.
Okay, so is this idea of normal ordering kind of like the same way as of like I guess I'm gonna try to drop the Fox space word again, but is it kind of like you could start counting with an infinite number of particles and then count down to 0 particles, or you could start counting at 0 particles and then count up to an infinity particles? Is it just like a way of, it's ordering your basis basically, right?
Oh yeah, this is creating our space of states, right? I mean, we've said we have these linear operators on some vector space. We have not defined that space yet.
Mm-hmm.
And it's only by having a consistent vacuum energy, some vacuum state, which we can now define as the one where a hat of k acting on that state gives 0, right? And this for all k, right? We can now prove that there is such a state because expectation values of the Hamiltonian are non-negative. That's not hard to show because the Hamiltonian is basically A dagger A. And A dagger A between a couple of any arbitrary state is the square of a state. It's the square of the state, you know, A state, and therefore is non-negative. So that means that eigenstates of the Hamiltonian are going to be positive or non-negative. And that means that there is such a state as this because we'll show that the commutator of H with A lowers the energy eigenvalue. So all the eigenvalues of H have to be positive, and yet A on an energy eigenstate is another energy eigenstate with lower energy. We can't do that ad infinitum, so at some point it has to give 0. So we have a well-defined vacuum in scalar field theory. And now what we do is we act with a dagger, and by computing the commutator of a dagger with the Hamiltonian operator, we show that a dagger raises the energy of any energy eigenstate by h bar omega. And so now we can act with any a dagger of k, and we can act with a dagger of different k's. We can act with as many a daggers of k as we like. So once we have that vacuum state, we can create things like, let's say, K1, 3K2. Okay, so here's a state where I have a dagger hat of K1 and a dagger hat of K2 cubed acting on the vacuum. All right, these all commute with one another. So I can write them any way I like, but this creates 3 particles with wave vector K2. This creates one with K1. So I have a state with 4 particles. And, you know, and I can step up any one wave vector as many times as I like. I can concatenate as many different wave vectors as I like, and I can build up arbitrary states that way. So these are my particle states. That's a particle state with 4 particles in it. And yeah, so hey, we've just built your Fox space. There you go. That's you know, as many particles as we like. So the arena, our space of states, is, you know, all n particle states, and those states can all have any wave vector that we want to assign to them. So now,
and then yeah, and Professor, then normal ordering is something like the vacuum state is always the first vector in each n particle subspace. Like your top left is your vacuum state, and then in your 2x2 matrix, the top left is the 2x2 vacuum.
Yeah, the vacuum is just a single state. There's only one of them, and yeah, and notice that now H acting on it, because we normal ordered H, H is just this operator here without the constant term. This operator acting on the vacuum gives 0. So H acting on the vacuum state is 0. It annihilates it. So there is no energy associated with the vacuum state. Now, you'll see all kinds of weird claims about that in the literature, like the vacuum is this roiling energetic place, and that gives rise to cosmological constants. And, you know, people go off with this in different ways, but notice that what we're doing is not odd in this case. Odd comes later, but we said even with the harmonic oscillator that there's an issue with normal ordering. Not normal order. There's an issue with operator ordering. When we impose the canonical quantization and take dynamical variables to operators, there is no canonical way classically to distinguish between x dot p and p dot x, but quantum mechanically they're different. So which do we use? Well, there is no prescription for that. We have just introduced the prescription for that. So this is how we're going to order operators. Anytime we're able to identify a vacuum and identify creation and annihilation operators, we know how to order states. Yeah, you know, I've tried to reverse engineer this and say, okay, so if I'm going to normal order A and A dagger, how do I write that in terms of our original phi and pi operators? I was not able to come up with anything conclusive. You know, you really, seems to me, have to have creation and annihilation operators well defined before you can actually define normal ordering. I don't know. I'd love to see a way to write this in terms of the original field and momentum, but I'm not sure there is one. It didn't translate well under reverse engineering, but yeah, maybe I didn't persist enough. In any case, that's how we deal with that first infinity. So now, let's see. The real question is how much of this you guys want to see. So, all right, it's not too hard to show that the Hamiltonian with A is a lowering thing. I could run through that in that's like 4 short lines. Yeah, that's not bad. Let's do that. You need to be able to actually compute those. And I'm thinking that unlike the exercises, what I've labeled problem 1, you'll see is like section 4. I forget what, 4.7 or 4.8 here. Yeah, section 4.8 is called problem 1. And that's the charged scalar field. And I'm gonna want you to hand that in. So work that out carefully, be prepared to send me a photo of your work or whatever. For now, let's compute H with A. So this is starting in the wrong part of the board, but H is D3K, H bar, let's write it as Q here, H bar omega of Q, A hat dagger of Q, A hat of Q, and then we want the commutator of that with A hat of K. Right, and this isn't so bad, right? We can do this because, all right, first of all, A commutes with A, whatever the K. So we have D3K, D3Q, H bar omega Q. I bring this past and we have A hat dagger of Q, A hat of K, times a hat coming out to the right. Okay, and now this is backwards, right? Our commutator goes the other way. So we're going to get a minus sign from this commutator. D3Q H bar omega Q del 3 of Q minus K A hat of Q. And that we just do the integral and we get minus H bar omega K A hat of K. All right, can everybody see it? Any question on that? Can you see it all right?
Yeah. Wouldn't the ordering of the delta function be switched? Would be K minus Q?
Delta is a symmetric function, so yes, but it's okay. Yeah, delta of Q minus K equals delta of K minus Q. So derivatives, however, are anti-symmetric, so be a little careful there. Yeah, if you're anticipating a derivative before you integrate, then be sure you're writing that order correctly. All right, so now, what this tells you, that minus sign tells you that this is a lowering or annihilation operator. that's that minus sign is the key thing here. If I had a dagger here, then the commutator would have been, that would be an A dagger, and I would have had to commute A with A dagger. That would be plus. So a dagger would give a plus here. And now acting on an energy eigenstate. So if I've got H acting on A, acting on some energy eigenstate, then I can write this as A acting on H plus the commutator HA acting on the eigenstate. And H acting on the state pulls out an E. So I have E A hat on the state. This we've just shown gives minus H bar omega times A hat, and that acts on the state. And so we have E minus H bar omega times that same state, A acting on the energy eigenstate. And so this combined state is an eigenstate with lower energy. And this shows that we can step down until the energy becomes negative, and that's not allowed because H has positive definite expectation values. So there has to be some state that H annihilates, that A annihilates. It's A that's stepping the energy down. I can do the same thing n times, and I'm going to get H minus n H bar omega. I could make that energy as low as I like if there weren't some cutoff. So there has to be a cutoff. And that's what allows us to define the vacuum state. There has to be some state that's annihilated by A. And given that state, we can now act with a dagger as many times as we like. That has the plus sign here. That increases the energy by H bar omega. And we're doing harmonic oscillators everywhere, but a lot of them. So a field theory, you'll see this again and again, that you're writing the same kinds of expressions that you write for the simple harmonic oscillator, but then you integrate that expression over all K. So I think I give an exercise to, let's see, do this that I just did for you. Well, okay, so there it is. Oh, no, I asked you to do it for a dagger. Well, that's 3 lines. That's an exercise again. I introduced the number operator. Did we just lose somebody? The number operator, just leave off the H bar omega. So it's A dagger times A summed over all K. That'll count the number of states. You can define a number operator for a particular K that will count the number of particles with wave number K. And then any set of those you could integrate over, or some integral over whatever set of K's you like, and find out how many particles there are in some wavelength range. And we're out of time. But any questions anybody has? How about it? So yeah, read through this. If you have any questions on carrying out those 9 integrals in writing the Hamiltonian, all right, read carefully through that section. Then you're going to do it again, for the charge field. But if you have any questions on that, we can put one up on the little board here. Yes.
Okay.
Alex, what you got?
Go ahead, Kevin.
Do you have a due date for that? Are you asking for that maybe like next Wednesday or something?
Yeah, let's see, later this afternoon. Yeah, let's aim for next Wednesday. You should be able to do that. Yeah, I did it all.
Are you going to post a formal?
Yeah, I did the
statement of
uncharged
problem?
case, yesterday in a day. So, yeah, if I give you a week, I think you can get through it. Yeah, I'm sorry. What was your question, Kevin?
Are you going to post a formal statement of the problem? Or
It's in the book. Yeah,
Yeah,
I'll
okay, yeah.
yes, I have written one up. I will post it.
Cool.
Yeah, in fact, I can put that up pretty soon. Let me think. I was just writing the last section of chapter 4, in which I look at the charge, and yeah, I deal with antiparticles too. Yeah, oh, that goes on a ways. All right, I'd better post what I've got and just tell you. Oh, yeah, we did lose Tyler, but he came back. Welcome back, Tyler.
Oh,
Oh, let's see. Okay, so there's a question in chat. What page in the book? Now, as I say, I haven't posted this yet, but the problem will start on page 126. Top of page 126 is where problem 1 starts. And, we can zoom over it, send me emails if you've got a short question on it, but be prepared to turn that into me next Wednesday. It's a real quantization of a field theory. So you ought to be able to do that. But yeah, you can run into some ambiguities. So don't hesitate to ask questions on it. Okay. Or anything else? Any other questions now?
Yeah. And then how about for a bound upper value of the energy? Is this maybe where you could extract?
Well, okay. So we can create n particle states for any n. Right. You give me any finite n and a list of associated wave vectors, we can create that state. Take the limit as n goes to infinity if you like. It could be that space-time is infinite. We don't know. But yeah, so we don't have any necessity. Oh, see it, Eli. Where'd you have it? Oh, there you
No,
are.
I just meant deus ex. Just say if we did have a bound energy value, then the creation operator has to annihilate, and then we'd get some finite set of eigenvalues.
Oh, yeah, that's right. If there were some state annihilated by a dagger, that would put an upper limit.
And then if we took that energy and divided by h bar and omega, then that would be like the n particle states, right? So is that a way to see the Fock space then, is just E is bounded at some integer multiple of h bar omega?
Well,
and then
if you want to put an upper limit on energy, yeah, that's what you would do. You would have to have some state annihilated by a dagger, and so hopefully that's a higher state than the one that's annihilated by A. So you'll get some state. So you start with a vacuum state, you act with as many A daggers as you're allowed before you hit that top state. Now you could still have infinitely many particles, because you could have A dagger to the n for each K. So you could have, n particles of wave vector K for every K. And so you still have an infinite number of particles in that state, if that's the way you say it.
Yeah, it would be, I guess the way I said it, you'd be picking a specific K, and then it could be specifically quantized to an nk. But then if you were fixing K too, you could add any different set of quanta. Right?
You could have different conditions for different K if you wanted. Let's say if you wanted to keep it's going to be hard to keep the number of possible particles finite, because K is a continuous variable.
Oh, yeah, if you let K vary.
Yeah. So you change K, you could have the same or a different upper limit, but whatever you set, you have uncountably many Ks. So, if there's a finite upper limit for each K, you're still going to have a divergent number of particles. Yeah, possible. Now, I don't know what would actually create that state.
Yeah.
But there are some very energetic sources out there, but not infinite. Well, they're the centers of black holes, I suppose. Those are pretty hot, but we also don't know what's there. Okay, other questions?
What did I miss when my internet connection went out?
Oh gosh, let's see. What's the last thing you heard? Yeah, I noticed you vanished, but let's see. But let's see. I guess. Well, yeah, we're still talking about raising and lowering operators, right?
Yeah. I definitely caught that. Let's see. Last thing for sure was we did all this stuff on the board. I remember that. I think we had just wrapped everything up, maybe. So I guess it's just like what any questions that were asked.
Yeah, I think Alex is wondering if there's an upper limit to energy, and
I got that. Yeah, I got that one.
So yeah, so if a dagger annihilates something, then you have to ask, well, how does that depend on K? So you would limit the number of particles of a particular K that way, but not the total number of particles, because K is a continuous variable. You have some finite upper limit for each K. You still can have particles of massively different numbers of K. Yeah, I mean, I've never seen anybody try to impose that kind of limit. If you want to keep your let's see, if you want to keep your Fock space to some low order of infinity, maybe you want to worry about that sort of thing. But yeah, I've never heard any. I have heard people talk about an upper limit to accelerations, and look at space-time models where things can only have a limiting acceleration, but limiting particle number is not really something that I've seen come up. So publish a paper. I mean, it's an interesting idea. You can make it concrete. Yeah, I don't know. Until you look at a problem, you never quite know whether it's interesting or not. But yeah, not sure what else to say about that.
Okay, yeah, I think the reason I'm digging into this is to get because they're to kind of see this picture like you do with the Glepsch-Gordon coefficients in the QM spin picture, where it's sometimes easier when you talk about transitions of like from a 5/2 to a 3/2 to all the possible 3/2 state to do that. It's that you do it in the, I guess you do it in the Fock basis, but where you say like 5/2, one 5/2 spin particle is like a 3/2 spin particle and a 1 spin particle, or you break it up. So the picture I'm drawing here is it's something like if for a total energy, and then we'll let energy go to infinity in the free case. If you picked a frequency K, you could get so many harmonics. So if you pick the frequency is at the energy, you get 1 state. Yeah. And then if you did half, you'd get 2 states, and then 3. And in that sense, you'd get block matrices on the diagonal of size 2, 3, 4. And then the total, all the possible states for any given energy would be like, yeah, you could have 1 in the top left, or you could have 1 in the second column and 1 in the, or 1 in the second and 2 in the fourth and fifth.
Yeah, you're describing something like the Planck experiment, where you have boundary conditions, so you only have harmonics of a certain frequency, right? And certainly for a bound state system, the number of Ks is countable. And there you another thing you have is equipartition of energy. So if you have a lot of particles, they're probably sharing energy, and you have some kind of envelope that limits the total energy. So that you could have a few high frequency particles or a whole bunch of low frequency particles. But you're probably facing some bounds there. There's a difference between thinking about Fock space and thinking about some physical system, right? So physical systems, we're talking about some finite number of particles. Fock space is a mathematical idealization where it's an arena where we can have any number of particles we like, and there's no particular reason to put an upper bound on that mathematical idealization. We use whatever part of it is convenient for a particular problem, and that lives down in the finite part of it. Unless you're contemplating like a spatially infinite universe, right, where you quite likely could have an infinite number of particles too, but the number of particles per unit volume is going to be finite anyway. So even then, you could normalize things to your local region of space-time, and you're always going to be dealing with finitely many particles. By the time you get huge numbers of particles, you're probably talking about string anyway. Okay.
Sure. Yeah, because equivalently, it'll be high enough energy that the lowest.
This model may not really work. You're certainly into a nonlinear regime anyway, where, if you're, let's see, what happens if we're dealing with gluons? One at high energy, one gluon begets 3 more gluons, and that goes on, divergently. So you really get things. You have to discretize to compute anything, in fact, in those circumstances.
I guess that's why you're having to do the annihilation operators for the Dirac field, is to see the subtleties with a higher spin field for that reason.
Well, yeah, I mean, we want to treat all fields. So yeah, we're going to, the Dirac field has complications beyond what we're facing with the scalar field. We're going to do these same procedures with spin half and spin 1. And by the time we've done the Dirac and the vector field, then we can do QED. We can start looking at interactions. We're just talking about free fields so far, right? So we know how to characterize free scalar fields. Like, fine, how many are there? Well, there's the Higgs. We're done. There's only, there aren't a lot of scalar fields around. There are a lot of fermions around. There are a lot of bosons around, spin 1 particles around. And the interactions of those are what we treat with Feynman diagrams.
And
yeah.
Sorry.
No, that's okay. There's, but each different spin field that you quantize, you end up introducing a little bit more new stuff. So, okay, we got our first infinity with just a simple scalar field getting a vacuum energy. Now, with the charged scalar field, we're going to see there's a conserved current. So in addition to the Hamiltonian, we're going to construct J and a charge operator that tells us how much electric charge we've got in the space. So there's an additional operator that we look at. Then when we go to Dirac fields,
presumably there'll be an annihilation and creation operator for that quantity, the charge too, then?
Yes. Yeah. There's a, well, it's the same A Dagger. So your charged field, you guys are solving, remember there's an A and a B, and one of those creates the antiparticle. So you've got an A dagger and a B dagger. And so what we'll find is the total current, or the total charge operator, is the basic charge E times the integral over all K of A dagger A minus B dagger B. It's the difference between the 2 particle numbers, because you're counting the number of particles and subtracting the number of antiparticles. It's just what you'd like to see. It makes perfectly good sense. And we derive it, from the classical expressions. We follow our normal ordering rules to write the quantum operator, and it all comes out right. Well, yeah, when we do a spin half field, it doesn't all come out right. And we're going to have to invent the exclusion principle. Okay. Yeah. So, we're going to make those guys anti-commute. Otherwise, things work out wrong. And so, each time you go up in spin, you encounter new things. When we do the electromagnetic field, you're going to find that, well, all right, your electric field, all right, you're going to look at what? Well, F mu nu, the Faraday tensor. So you've got A mu, but there's gauge freedom. And so how do you handle the gauge freedom, even at the point of computing the conjugate momentum? There are really only 3 conjugate momenta, not 4. So there are various tricks for handling that. So we're going to add to the story here as we go along. And then we get all our free fields for various spins. Now we add interactions, and how do we handle that? So yeah, there's lots of ground to cover here. So it's important to do problem 1.
Yeah,
right?
yeah.
Because everything else is going to be doing that again and again and again, but with more nuances, more complications. But it's really cool how much you end up predicting. Like Dirac fields. They really need to anti-commute, or let's see, what is it? The operators that measure measurable properties like energy and spin and stuff come out with the wrong signs. So you need to fix it somehow. And the fix means that you can't have 2 particles in the same state.
Okay.
Yeah.
Okay.
All right. So go off, compute. I'll get this. I'll get this posted. This afternoon. Pretty soon. I don't see any reason I can't post at least up through section 4.8, which is problem 1. And yeah, I'm still working on the last couple sections there, but I'll describe where I am when I post it. So that'll be online. Tyler, you got any questions?
Nope, I was just kind of listening along. So
yeah, sure, for sure.
Yep, yeah. Sounds good. We'll talk to you next week then.
And everybody else can too, because I recorded all this. Okay. I'll see you then, Tyler. Take care.
We'll see you around.
Okay. So.
And I think thanks. Yeah. Unless there was something from earlier that was worth talking about. That was maybe my only